We should move towards Mark Alexander, that also is very well experienced in the use of indicators. Thanks, Mark, for participating.
Thank you. Thank you very much, Carmen, and all the participants. It's a great pleasure for me to be here this afternoon and to present some of our own background in the South African durability index approach. That word index can be taken to be identical with indicator. It's just the word that we have used consistently over the years, but let's not be concerned here too much about semantics. Index and indicator can cover for the same idea. If I can also just mention that this approach that I will briefly share this afternoon has actually been in existence for more than 20 years in our country. We developed this in the late 1990s and early 2000s. It was written into specifications of our National Road Authority, for example, and many other specifications, and has therefore been an actual implemented scheme over that period of time. In that regard, it doesn't necessarily fulfill all the requirements that we heard earlier from Steinar, but it has the basis for doing that. And as I said, it's a scheme that is in action and has been in action. So the test methods, for example, have become national standards and so on. You'll also see quite a bit of similarity here with what Roberto shared, and also to some extent with what Veronique was sharing just now. So in the work that we've been engaged in, right from the beginning, we wish to provide a framework for the designer to establish a required level of performance. So you can see these words being interchanged here to some extent, and also within which the material producer and the constructor can produce a structure of desired quality, and also then that the owner can be assured that the quality desired is actually achieved. So in our scheme, the loop has to be closed by the structure itself being tested. And we'll come a bit to that later on as well. So it's a sort of there's a closed loop involved here from design through to final construction and to clarification or to verification of the final structure itself, obviously on a sampling scheme. And this is what we call the durability index approach. And the ultimate objective is very much what we see within the standards developments, performance-based set of durability design and specification protocols. So it is premised upon a performance-based design. And in such an approach, one has to verify that performance, not simply on, let's say, lab or sort of model type concretes, but on real structures, and then ultimately frame these in a fully probabilistic approach, which leads us to measures of reliability. This was the scheme we started off with actually a very long time ago. And in this very busy slide that I put up here, I don't expect you to read the whole thing, but there are a number of key boxes here, if you like, or sections of the slides. First thing is what we call the material indexing, which is what we'll deal with mostly this afternoon. And I'll come and define that a little bit later. However, this is linked at the bottom there with structural performance. So while one studies the material, one must also study the structure and find out what's going on in the real structure and how it's deteriorating, and link the two. These can be also used, this approach can then be used obviously for quality control. And if one can link in the environment, which is very important because durability is not something that you can speak of in isolation of the environment, then you can also move, as I've just indicated there, to service life prediction. So by bringing all of these together in one common scheme, sort of a philosophical scheme, one can make progress along this path. And so these are our premises upon which we've worked. First of all, if we're going to improve the durability of reinforced concrete structures, then in our case, the durability indexes that we speak of deal with that issue, durability of reinforced concrete structures, and that largely comes down to reinforcing steel. So we're not dealing here with durability indicators to do with, say, alkali silica reaction, soft water attack, sulfate attack, and so on. This is purely to do with steel corrosion issues. And that comes down to the quality and quantity, or thickness, if you like, of the concrete cover. We have to characterize those two aspects of the concrete very, very carefully. And then we will not improve our durability unless we can measure something relating to the quality of that cover layer. We must be able to measure it, and if we can measure it, we can control it. Also, the cover quantities, or the thickness in the scheme, is also a requirement for testing cover on every structure in a certain sort of sampling scheme. That's the other side of it, which I won't deal with here in these set of slides. And so we've developed tests to particularly reflect the quality of the cover layer, and we call them durability indexes or indicators. And we define them as follows: that a durability index is a quantifiable engineering parameter that characterizes concrete durability, or very broadly, quality. So we're measuring things at the engineering level, things that can be understood within an engineering context, bearing in mind that mostly what we're dealing with here is structural engineers who want fairly simplified, although not non-rigorous approaches, but things that can be applied in a fairly simplified way. These indexes must be sensitive to the important factors, that we the material factors, the processing, so that means the mixing, placing, and finishing and curing, that's processing parameters, and the environmental factors. So they should be sensitive to those things. For example, curing time would be one. They should be based on the measurement of the transport properties. There's an important word. So we have to characterize transport here, not simply mechanical properties, but physical and transport properties, to some extent chemical properties of the cover layer. And that should be able to be done in the lab or on the in-situ concretes. So we have to be able to close that loop between the lab and the real structure. So as we mentioned, they're linked with transport mechanisms, and those transport mechanisms relate to the mode of deterioration. So for example, if we're dealing with carbonation-induced corrosion, then we want to have a measure of gas transport. And then through service life models, we can then move to durability design. So let me review briefly the tests and the service life models. There's a whole section on implementation, but I won't go into that this afternoon. So this is the OPI test, the Oxygen Permeability Index test, that was developed in the late 1990s. It's a very simple test. It's a falling head permeameter in which a specimen is clamped into a specimen chamber. One charges the cylinder with gas, oxygen in this case, measures the pressure decrement with time, and within the space of not more than 6 hours, you get a result which is related to the Darcy coefficient permeability. The specimen is obviously preconditioned in a certain way, and the specimens are roughly 70 millimeters diameter, 30 millimeters thick. And the reason for that 30 millimeters is roughly to characterize the cover layer. Remember, it's the cover layer that is of concern to us here, not the bulk of the concrete. So this cover layer is very sensitive to all kinds of things, and we have to characterize that particularly rather thin section of the overall structure. So the OPI is defined as the negative log of Darcy coefficient, just to make it into a more easily wieldable number. And the common values would be between about 8.5 and say 10 or 11, which on a log scale gives you nearly 3 orders of magnitude, which you would expect. And we use this to control carbonation resistance. And the Darcy, the equation is given there, and the K value, or the OPI value, which is the log of the K value, is linked to the carbonation diffusion coefficient. That allows us then, as you'll see in the model just now, to do some modeling of carbonation ingress. Okay, so let's move on to the next one, which is the chloride issue. This is the other major reason for reinforcement corrosion, as we're all well aware. And in this case, 25 years ago, we developed this test called the Chloride Conductivity Index test, which is a South African standard. It's really based on the chloride permeability test, the ASTM test. But what we did here was that we used a specimen in which we saturated the pore solution with a sodium chloride solution so as to eliminate the influence of the pore structure, as it were, and we were able to pick up the intrinsic characteristics of the material itself. So this is a test. Again, you have to condition the specimen, but once the test is in the rig, it takes no longer than about 10 or 20 seconds to get a result. So it's a very rapid test, and the values come out in millisiemens per centimeter, typically between 0.5 and 2.5 millisiemens per centimeter, which represents quite a large range of chloride resistance of the concrete. And again, using the very well-known fixed second law, the chloride conductivity is linked to the diffusion coefficient. And then knowing the surface concentration, we can work back to a chloride value and therefore a chloride profile. And in that way, one can start to understand what's going on. And one can also use it, of course, to quality control by limiting that chloride conductivity index in the structure itself. And so that leads on to the models that have been developed. These are very simple models. More complex ones are being developed now, but really these simple models have worked extremely well for us over the period of time. They're initiation models at this stage. There's one for carbonation resistance, which we use the 28-day OPI as a parameter, and one for chloride resistance, which we use the 28-day chloride conductivity as input to a Fickian model. We have to make some modifications there for chloride binding by effectively aging the value. But that we could talk at a separate time if needed. These models account for material type and environment, importantly, and it's an integrated approach, or this kind of closed loop. We use it in design via the service life models, in specification, in which minimum required values are given, with the number of defectives that are allowed and so on, and then for quality control, checks on the as-built values, and in this case, there are also penalties that are built in for not meeting these values. So the contractor would have to pay penalties if the values are not met. This is a very quick look at the carbonation model. You can see here the correlation between the Darcy coefficient on the x-axis and a carbonation diffusion coefficient on the y-axis. And this represents a series of different concretes made of different binder types. And there's a very good relation there. So we can relate this OPI parameter to a diffusion, kind of a carbonation ingress value. And this is very helpful. It can handle things like different relative humidities, the time of wetness of the system, as well as the ambient, environmental carbon dioxide concentration. And just as a matter of interest, we work quite closely with Roberto Torrent and trying to compare our approach, which is based on little core specimens, as I mentioned, and his direct in situ approach, and found very good correlations between the two approaches. So here we have the KOPI on the bottom axis, and on the vertical axis we have KT value, and the different classifications are given there in terms of the terminology that have been used, but you can see the pretty good tie-up between those two. And the intent here would be, in the end, maybe to move to the Torrent test for this particular type of problem. And if that showed that the structure did not meet the requirements, we could then resort to our approach, which involves removing a small core from the structure, taking it back to the lab and conditioning it to an absolutely uniform moisture condition, which the Torrent test doesn't allow you to do all that easily. The chloride surface life model is based largely on the formation factor equation like that, the one that you see there. So in other words, if we can measure conductivities, we can infer diffusivities. And as I said, we need to allow for an aged effect because of binding. And a nomogram has been developed in which one can enter the chloride conductivity value, move through the binder type and the environment, however you want to define that, and come up with a diffusion coefficient, which can then be applied in a service life model to check on the diffusion on the chloride profiles. And just to give an example of that, this is the spreadsheet. It's implemented on a very simple spreadsheet, which doesn't need much by way of computing power at all. And here you can see a chloride conductivity of about 1.5 millisiemens per centimeter and a 5% surface concentration at 50 years would give those parameters as we have there, different diffusion or exposure types. And this is a ground granulated blast furnace slag concrete. So you can see there that the typical 0.4% limit is achieved at, say, around 60 millimeters of cover. That's at 1.5. If you then reduce that chloride conductivity to 0.5, a much better quality concrete, so now you've got a much lower water binder ratio, then you can bring that down to, say, half that value, about 30 millimeters. And so here, by improving the quality of the concrete, you can get a much lower value for that profile, and you would need a lower cover to achieve the same life. And so you can actually rationalize, you can also optimize between quality and quantity. So it may cost you more to create a better quality concrete, but you can save on, let's say, the amount of cover you need. And that would then give you an economic balance if you wanted to do that. So you can do both technical and economic optimization. So that's how it sort of works. And I think that to close off, let me just then go back to the requirements for establishing this performance criteria. It's very much like Roberto shared. We must have robust quality control tests. These have to be easily carried out, routinely done, reliable measures of resistance. We need service life models, which should relate to that quality control test. We have to close that loop in order to have an integrated scheme. We must be able to account for what we call margins or differences, because you get what we call a material potential. That's what might be produced by the ready mix producer. And the as-built values, invariably, the as-built values in the real structure are lower or of lower quality generally than the material potential, which is what the ready mix producer produces. And so to differentiate between areas of responsibility, and hence also a question of payment items, those two have to be differentiated as well. Otherwise, you're continually having conflicts between these issues. And I guess that's enough from me for the moment. So thank you for your attention this afternoon.
Thank you, Mark, for your presentation and how you have condensed. Thank you very much.